All right, let's dive right in. Today, we're going to get into the absolute heart of how machines actually learn. We're talking about an algorithm with a pretty fancy name, backpropagation. But trust me, the idea behind it is something we can all wrap our heads around. So let's get ready to peel back the layers on this amazing process.
So picture this. You've got a machine, a neural network, with millions, sometimes even billions of these tiny little knobs or settings that it can tune. When it gets an answer wrong, which it will a lot, how on earth does it know which of those millions of knobs to turn and which way to turn them to do better next time? That right there, that's the fundamental puzzle we're going to solve today.
Okay, so first things first. Before the network can even think about fixing its mistakes, it needs a way to measure them. I mean, it has to know just how wrong it is, right? And that's where this thing called a cost function comes into play. You can think of it like a final grade for the network's overall performance. It looks at everything the network did, compares it to what it should have done, and boils all of that down to one single number. A high number, that's a bad grade, lots of mistakes. A low number, hey, it's getting things right. And the entire goal of learning, the whole game, is to get that single number as low as possible. So you can almost picture the learning process as trying to find the very bottom of a huge, complicated, hilly landscape. Every single spot on that landscape is a different combination of all those millions of knobs, and the altitude of that spot is the cost, or how wrong the network is. Our job, it's to find the steepest path downhill from wherever we are, and that, in a nutshell, is exactly what backpropagation helps us do. Now, trying to think about all those adjustments across thousands of different examples all at once, well, it's pretty mind-boggling. So to make sense of it, let's zoom way in. Let's just focus on what the network can possibly learn from one single mistake on one single training example. In this case, a handwritten digit 2. Okay, get this. The network is just starting out, so its outputs are basically random guesses. What we really care about here is the gap between what the network is saying and what we want it to say. See, we want the neuron that represents the number 2 to be shining super bright, a value of 1, but right now, it's really dim, only 0.2, and at the same time, some other neurons, like for 1 or 3, are way too bright when they should be off. This is the mistake we need to fix. So you can almost imagine that each of these output neurons now has a desire. The 2 neuron is sitting there thinking, I need to get brighter, a lot brighter. And all the other neurons for 0, 1, 3, and so on are thinking, whoa, I need to get dimmer. So now, based on this one single mistake, the network has a clear list of goals. And this is where the magic really happens. Instead of trying to guess how to make changes from the very beginning of the network, we start at the end, with the mistake itself, and we let those desired changes ripple backward through all the layers. Let's just stick with that 2 neuron that wants to get brighter. How can we make that happen? Well, there are basically 3 levers we can pull. We could just increase its own internal bias, kind of making it naturally more eager to light up. We could increase the strength or the weights of the connections that feed into it. Or, and this is the really cool part, we could change the brightness of the neurons in the layer that came before it. Now here is a really key insight. Not all of those changes are created equal. You don't get the same bang for your buck with every adjustment. Think about it. If a neuron in the previous layer is already shining brightly, then strengthening its connection to our 2 neuron is going to have a huge impact. But trying to strengthen a connection from a neuron that's barely even on, that's not going to do much. So the algorithm is smart. It prioritizes the changes that will be the most effective. This leads to a really powerful idea, and it's summed up by a loose but super useful analogy from neuroscience. Neurons that fire together wire together. In our case, it means that the neurons in the previous layer that happen to be active when we're looking at a 2 are going to get their connections to the 2 output neurons strengthened. The pathways that contribute to the right answer literally get stronger. So the desire of that 2 neuron to get brighter, along with the desires of the other neurons to get dimmer, gets calculated and then passed backward. This creates a whole new to-do list for the previous layer of neurons. Now that layer knows which of its own neurons need to get brighter or dimmer to help the final layer out. And this process just repeats, this wave of desired changes flowing backward, layer by layer, all the way to the very start of the network. But hold on. There's a big problem here. If the network only listened to the demands of this one single 2 image, it would just get really, really good at recognizing that specific 2. It wouldn't learn the general idea of a 2, it would just memorize one example. And that's not learning, that's just cramming for a test. The reality, of course, is that the network isn't learning from one image. It's learning from thousands, even tens of thousands. You take a classic data set like MINST, which is for handwritten digits, and you're looking at around 60,000 different images for the network to learn from.
So here's how it really works. The algorithm figures out all the little nudges that the 2 wants. Then it does the exact same thing for a 7, which you can imagine wants a totally different set of changes. Then it does it for a 9, and so on, for every single image. And then, and this is the wisdom of the crowd moment, it averages all of those thousands of conflicting desires together to find one single balanced adjustment, one small step that hopefully makes the network just a little bit better for all of them. But as you can probably imagine, this brings up a huge practical problem. Going through all 60,000 images just to figure out how to take one tiny little step downhill, that would be incredibly painfully slow. So in the real world, we use a very clever shortcut. Instead of using all the data for every single step, we do something called stochastic gradient descent. We just grab a small, random handful of images, say 100 of them, called a mini batch. We calculate the average downhill step just for that tiny group. Now, is it the perfect direction to go? Nope, but it's a good enough direction, and it is way, way faster to calculate. The analogy for this is just perfect. It's like the difference between a careful hiker who meticulously calculates the exact perfect downhill path before taking one slow, careful step, versus a drunk man who just kind of stumbles quickly in the general downhill direction. He's messy, he's not precise, but you know what? He gets to the bottom of the hill a whole lot faster.
So we have this absolutely beautiful, elegant algorithm that can learn from its own mistakes. But if you take a step back and look at this whole process, from measuring the error to working your way backward, the entire thing depends on one critical, absolutely non-negotiable ingredient. So, to recap really quickly, backpropagation is this incredibly clever algorithm for finding the fastest way to reduce the network's error. It works by figuring out the desires from a single mistake and sending that information backward. Then it averages those desires over tons of examples to find a good general direction. And finally, it uses that drunk man's walk shortcut to actually be useful in the real world. The math is beautiful, the process is surprisingly intuitive when you break it down, but it all hinges on one thing. The network can only learn from a mistake if it knows what the right answer was supposed to be in the first place. So what is the one thing this whole incredible learning machine cannot function without? The answer is data. And not just any data, good, clean, labeled data. Because without that correct label, there is no mistake. And without a mistake, there is absolutely nothing to learn from.